Yellowstone Eruption Hazard Assessment, Pyroclastic Flow and Volcanic Ash Distribution Study. This study explores the potential hazards of a future Yellowstone supereruption by analyzing the dynamics of pyroclastic flows and the distribution of volcanic ash across North America. Utilizing geological records, geophysical models, and satellite simulations, the assessment aims to evaluate eruption magnitude, atmospheric dispersal patterns, and the likely impact on ecosystems, infrastructure, and global climate. The results highlight the need for continuous monitoring and robust hazard mitigation strategies in anticipation of possible large-scale volcanic events. Yellowstone National Park sits atop one of the most active and complex volcanic systems on Earth, a colossal caldera that has experienced 3 cataclysmic eruptions over the past 2.1 million years. The most recent, approximately 640,000 years ago, expelled over 1,000 cubic kilometers of material, reshaping the regional landscape. Despite its current dormancy, seismic and geothermal activity within the caldera suggests that Yellowstone's magmatic system remains active. Understanding potential hazards from pyroclastic density currents, PDCs, and volcanic ash fall is critical for disaster preparedness and risk reduction. Geological framework of the Yellowstone caldera. The Yellowstone hotspot is fueled by a deep, mantle plume that drives extensive magmatic activity beneath the North American plate. The current caldera, measuring roughly 70 kilometers by 45 kilometers, contains a shallow magma chamber composed of alternating layers of rhyolitic melt and crystalline mush. This structure determines eruption behavior, influencing both eruption style and dispersal. And pattern-not geophysical surveys have identified zones of partial melt at depths of 5 to 15 kilometers, suggesting a volatile, rich system capable of generating explosive eruptions. Thermal anomalies, uplift patterns, and hydrothermal disturbances indicate ongoing pressurization within the system. Pyroclastic flow hazards. Pyroclastic flows, fast-moving, high-temperature avalanches of volcanic gas, ash, and rock, represent one of the most devastating aspects of a supereruption. Simulation models indicate that such flows from a Yellowstone-scale event could extend over 100 kilometers from the vent, engulfing vast portions of Wyoming, Montana, and Idaho. Temperatures exceeding 500 degrees Celsius and velocities surpassing 300 km/h would obliterate all organic and built structures within the affected region. The potential for pyroclastic surges to cross topographic barriers further amplifies their hazard. The thickness of ignimbrite deposits, as observed in the Lava Creek Tuff, provides physical evidence of the intensity and reach of past pyroclastic events. Volcanic ash distribution and atmospheric transport. Volcanic ash from a Yellowstone eruption could spread across continental scales, significantly disrupting air traffic and agriculture. Ash dispersal simulations based on prevailing westerly winds predict accumulation exceeding 1 meter within 300 kilometers of the source, with measurable deposits reaching the eastern United States. Fine ash particles injected into the stratosphere could remain suspended for months to years, leading to global climatic effects including solar dimming and surface cooling, a phenomenon known as volcanic winter. Data from tephra deposits in the geologic record show that Yellowstone ash layers have been identified as far away as the Gulf of Mexico and the Atlantic Ocean, illustrating the immense reach of past eruptions. Environmental and societal impacts. The immediate consequences of a large Yellowstone eruption would be catastrophic. Local effects: destruction of habitats, loss of biodiversity, and incineration of forests. Regional effects: collapse of infrastructure, widespread respiratory health hazards, and contamination of water systems. Global effects: reduction in global temperatures by 1 to 3 degrees, crop failures, and prolonged atmospheric opacity affecting photosynthesis. The eye. Eruptions' socio-economic repercussions would likely surpass those of any modern natural disaster, affecting global trade, agriculture, and climate stability. Conclusion. Yellowstone's potential for a future eruption represents a low probability but high consequence event. The combined effects of pyroclastic flows and widespread ash distribution would cause unparalleled regional devastation and global disruption. Continued research on magma dynamics, eruption precursors, and atmospheric processes is critical to refining hazard models and improving resilience. Understanding Yellowstone is not merely a matter of scientific inquiry, it is a necessity for global preparedness in the face of Earth's most powerful natural forces.